So, hello, everyone, welcome back. So finish our midterm this week, but the midterm is still under grading, so we'll postpone the explanation and I guess your questions about of midterm to Friday. I think we are doing grading on Wednesday, and hopefully we'll have something finished on Friday, but even if we didn't finish our grading on Friday, we'll have an explanation. I think the first half of the Friday will be explanation, and then we'll continue teaching chapter 4 on Friday. Okay? And since the midterm is still under grading, let's moving forward a little bit and talk about continuous time Fourier transform. Okay? And so I guess let's go to this page. It's a bit more easier. Okay, so the idea of continuous time Fourier transform is that it's a frequency representation of a periodic signal. Okay, so remember in chapter 3 we talked about Fourier series. So we talked about continuous time Fourier series and discrete time Fourier series. And but for Fourier series, Fourier series are nice, and here is a bit spoiler. So Fourier series is where you write a periodic signal as its harmonic components. Okay, so the idea of Fourier series is we want to write our function as some linear combination of those complex exponentials, because complex exponentials are easy. Okay, and we have done this for every periodic function. So every periodic x of t. With some period big T, then we say, well, not every periodic function, but most of them, we can write it as we can write it as this linear combination, this synthesis equation, is some ake to the jk omega naught t, where this e to the jk omega naught t once again are the harmonic components. And then how you find ak is you can do this analysis equation, is 1 over t, and integral x of t e to the minus jk omega naught t dt. Okay? And but this is only for periodic function or periodic signal. And in chapter 4, so we want to ask what if we have a periodic signal. Okay? So we have a periodic signal, and we still want to express them as this linear combination of complex exponential. And turns out what we get is this Fourier transform. Okay? So this is a famous Fourier transform. And the Fourier transform, we told this in a slower pace. So in chapter 3, we have both the discrete time and the continuous time Fourier series. But for Fourier transform, this whole chapter 4 will be only continuous time Fourier transform. And chapter 5 will be the discrete time Fourier transform. Okay? And the idea of how we derived this Fourier transform is we start with the Fourier series. So those two equations we already know. And we just take this big T period to infinity. Okay? So we say, wrong way. So we say when we take big T to infinity, then if your period is really long, then your periodic function really looks like a periodic function. That's basically what happened. It's kind of a sketchy derivation, but this is what they believe, and we'll derive some very clean equation at hopefully end of today. Okay? And so we have the definition of continuous time Fourier transform, and we will have, once again, it has convergence issue, kind of because we are in continuous time. So we'll convergence issue, and we'll have the Dirichlet conditions to say, if you satisfy the Dirichlet conditions, then your convergence is pretty good. Okay, so once again, we start with this Fourier series. So what happened is, one thing here is instead of this in this Fourier series, we start with this periodic function x of t, and we kind of transform it to this discrete numbers ak. Okay, discrete points ak. Okay, so we kind of transform between x of t and ak, and we label things by k. And but now this is a very rough idea. One thing we can look at is instead of looking at the k, maybe we should look at the k omega 0. Okay? So this is basically what we will do today. Is instead of k, we look at k omega 0. And I want to say k omega 0 is something worth looking into, because if you think about x of t as the sum of those harmonic components, then k omega 0 is actually the frequency of this harmonic component, right? This is how fast this complex exponential is oscillating. Okay, so k omega 0 is very important, and it's a frequency of a harmonic component. And so what happens is we'll take t get bigger. So I should write this, but anyway. Okay. So what happens is we'll take so we'll get this big T bigger, then omega 0 will get smaller, and then we'll get the finer sampling points on those k omega 0. Okay, and yeah, and just as one more one more motivation to regulate the k omega 0. So remember at the end of last chapter we talked about how the LTI system responds to some input of this phone already in Fourier series, and we see that you apply this big H function also on k omega 0. Okay, right? And we even have a midterm problem to asking you about this filtering, right? And when your H is a filter, and you will determine whether a component get filtered out or filtered out or not, depend on this k omega 0. Okay, and yeah, so we'll see how we express everything in k omega 0. And we start with, okay, so we will kind of do this twice. So we start with a specific example. So this is a periodic signal that we already do is Fourier series representation. Is a square wave. Okay. It's a square wave signal, and we have calculated its Fourier series expression. And Fourier series coefficients. So the Fourier coefficient AK, we calculated as is sine k omega 0 over k omega 0 sin k. And more explicitly, so AK we calculate as 2 sine k omega 0 t1 over k omega 0 t. And so here you kind of see that all the k omega 0 are together, and we can I guess change the interpretation of AK a little bit, or like change the normalization of AK a little bit. So if we just multiply big T on both sides, so we have T, big T times AK here, and the other side you see is a function of 2 sine k omega 0 T1 times k omega 0. And if you think, if you just name k omega 0 as another function, another variable omega, and then you see that this side is independent of big T. Okay. Okay. And we can so if we plot this, we can kind of plot this TAK function. So you see the TAK function. If you plot it as a function of omega, then it's it's just this function of omega is independent of T and independent of K. Okay. So the 2 sine omega T1 over omega function is just a fixed function here. Okay. And yeah, 2 sine omega T1 over omega is just this envelope function is staying the same. And so you can kind of get your AK from this. You can get your AK from this envelope function, which doesn't depend on big T and doesn't depend on K. And so what you do get AK is you kind of sample on this envelope function. So you think about omega, this k omega 0 is, well, so omega equal to k omega 0. So at some k, right? So you think about, so when you fix some big T, then you will get some omega 0. And you kind of find the k omega 0 on this omega line. So say here you have a median size omega 0 here, right? So this spacing here will be omega 0. Okay. So here we have some middle size omega 0, and so this point will be 1 omega 0 and 2 omega 0 and 3 omega 0, 4 omega 0 as we see here. Okay. So you find your k omega 0 here. So maybe k equals 6. Here, okay, so and so you will see big T AK will equal to this point, and then you want to find the AK, then you divide big T. You divide this number by big T, And so you see that when big T gets larger and larger, you're actually sampling these envelope points in finer and finer grid. And we'll think that when T goes to, so when big T goes to infinity, you are basically sampling every point on this envelope. And so all the AK are actually, the information about AK is actually just this envelope function, TAK. Okay. So yeah, so this is what happened. So we think because this TAK function is something independent of your big T, and so this TAK function is actually represent this big TAK function actually represent every frequency component of your XOT when T goes to infinity. Okay. So that's a rough idea. I guess. Any questions so far? Yeah. 什么东西？sorry，RHS 是 right hand side， 这是右手侧，对 ，yeah right hand side。Okay, yeah. So that's the envelope function and the kind of sampling, and yeah. So rough idea is as big T goes to infinity, we are sampling every point on this envelope function. So we just think this envelope function is some kind of a frequency domain. So this omega is the frequency. Remember, TAK is remember omega equal to k omega naught, and we spent a few minutes talking about k omega naught being the frequency of the component. Okay, so we will see that when big T goes larger and larger, we are sampling those frequency components in finite and finite grid, and as T goes to infinity, then we are basically sampling every omega point, and then this TAK will represent the response or not quite response, represent every frequency component of our aperiodic signal. Okay. And yeah, and so this is what happens when we see this in square wave, and we now try to get I guess a very rough sketch of derivation on general signal. Okay, so now we have a periodic signal, and let's assume it has a finite duration. Okay, so not quite every signal, but a very general class of signal is a periodic signal has some finite duration, magnitude T1 to T1. Okay, and yeah, and then we try to represent it as linear combination of complex exponentials. Okay, and we don't know quite how to do, so we try to start with the Fourier series. So what we do is we make a periodic signal out of this aperiodic signal. So this x of t is something finite duration. So this is not periodic. It just has some form here, and we just repeat it. So repeat this to construct a periodic signal x tilde of t. Okay. So x tilde of t is you just copy paste x of t and at the positive time and the negative time. Okay. So x of t, because it has some finite duration minus t1 and t1, so you just pick your period, big T bigger than x of t, then you can paste those finite durations there's far apart with each other, and this becomes a periodic signal. Okay. So extend this to minus infinity and extend this to plus infinity. Okay. And now x tilde of t is the periodic function, then we can use our favorite Fourier series equations. Okay, so we have our synthesis equation and our analysis equation. Okay, and yeah, so we write those two down for our x tilde of t. So x tilde of t is some ak for some ak e to the jk omega naught t, and where is ak is 1 over t, and integration 1 over 1 period x tilde of t e to the minus jk omega t dt. This is just writing down those two equations. Okay, and so obviously this omega will depend on your big T chosen. This omega naught depend on the big T chosen here. Okay, and so now we start doing something funny. So we try to mimic the envelope function here. Okay, and so aka of t, aka is this 1 over t integration x tilde of t times e to the minus jk omega naught t. Okay, and then one thing happen is we see this is ak is done by integrating x tilde of t over one integral. and we choose this from minus t over 2 to t over 2. So something like here. Okay. So ak is this integral over one period, and for x tilde of t. But we see that over this one period, x tilde of t actually equal to x of t, because that's how we construct it. We have this one period. In one period, x tilde of t also always equal to x of t, and it's just copy paste x of t to other period. Okay. And so in this integration, instead of x tilde of t, we can write x of t. And then something funny we do is, so instead of integrating from one period, because now we're integrating x of t, and so back here, so x of t, you're integrating over one period is the same as you're integrating over the whole line, right? Because integrating outside of this period is O0. X of t is O0 by construction, by definition. Okay. So instead of integrating over one period, we can integrate from minus infinity to plus infinity. And then just like in the square wave case, we multiply big T on both sides, and we see that this big T AK function, this envelope function is something really nice. Okay, is big T AK function, which we define as j omega. Has this clean form minus infinity to integration minus infinity to plus infinity, and our x of t here, and e to the minus j omega t dt. Okay, and yeah, I guess this is a function of k, but now we change a variable. Okay, I guess we forgot to say something here, and we also define omega equal to k omega, just like we said before. Okay, this is important. And so we also change. Okay, so we move t to other side, and we think about this function tak. And instead of a function of k on both sides, we think it as a function of omega. Okay, and so this function of omega, which we call big X of j omega. You see that, well, is indeed of a function, just a function of omega is independent of big T. Okay. Okay, so this is a function minus infinity to plus infinity x of t to the minus j omega t dt. And yeah. Okay. Okay, so we have this nice big X of j omega function. And I guess let's do a small digression here. So why do we call this big X of j omega? So x of j omega is kind of related to very beginning. So where we do filter, it's kind of related to why we call this big H of jk omega naught instead of a big H of k omega naught. Right? Because we think it is complex exponential. Yeah, it has this number being purely imaginary. Okay. So big H, so this big X of j omega naught, this big X of j omega, this j omega correspond to, it's a component for e to the j omega t, right? This is kind of the coefficient for e to the j omega t, so that's why you have a j here, okay? I guess we'll see this a bit in more detail later, okay? Anyway, this is our big X of j omega. And so this is actually so a bit spoiler, this is the Fourier transform of our small x. Okay, so we have our small x is a function of time, and now we have this big X as a function of frequency. And this actually has every information of the small x. And now we try to express everything in terms of this big X. In particular, we want to have a reverse equation. We want to express small x as big X. Okay, so what we do is funny. Okay, so we try to express small x as big X, and what we do is we go back to these two equations. Okay, so yeah, so we want to express small x. Well, it's actually this. Okay, we want to express small x through ak, and we can. So what we do is we express ak as big X, then we express small x as ak. Okay. Let's see how this works out. Okay. And so first we express ak as a big X. That's easy because it's basically by definition ak is big X divided by t. Okay. And but ak is a function of k, so we write this big X as a function of k instead. Okay. Okay, so AK as 1 over t big X over JK omega naught, and then we can express X tilde as AK. This is just our synthesis equation. Okay? So X tilde is summation AK e to the JK omega naught t. Okay? And yeah, and then we have this 1 over t here, and for convenience, for reason we'll see very soon, we express this 1 over t as omega naught divided by 2 pi. Okay, so 1 over t is omega naught divided by 2 pi, so nothing will happen. Okay, and so we have this X tilde of t equal to 1 over 2 pi summation k big X of JK omega naught and e to the JK omega t omega naught. Okay, and now we take our limit of big T to infinity. Okay, and we think big T to infinity, X tilde of t should become X of t. Okay, that's because, let's go back to this picture, because we think about X tilde of t is copying of X of t every big T. So we think if you push this big T to infinity, so all those copies are really far away, then really this X tilde looks similar to X of t. This is not very rigorous, but this is a sketch of what we think. Okay, so as big T goes to infinity, X tilde of t should equal to X of t. Should go to X of t. And what about this summation? So we think this summation will become an integral. And this is actually kind of rigorous, because this summation, you think about it, it has, if you try to plot this summation on this X over j omega e to a j omega t line, e to a j omega t graph. So let's first plot, we think about this function that's big X of j omega e to a j omega t. Okay, and it's a function of omega. That's kind of important here. Okay, so we think about this function, then you see that okay, so this is a function of omega, and this function is big X of j omega and e to a j omega t. So remember, the k omega naught is kind of like omega sample at a discrete point. Okay. And yeah, so you see this summation is actually a approximation of integration. So this is an approximation of area under this curve. Okay, because each so each term in this summation is rectangular. Okay, so its height you can think of this as a rectangular with height being, well, is e to a j omega e to a j omega t simple as omega equal to k omega naught, right? So yeah, so here we have an example. This is a textbook example. So we have k omega naught here, right? So this point here will be, the height will be e to a j k omega naught big X j k omega naught e to the j k omega naught t. And so this is the height, and this is the width, right? So the width is omega naught. Okay, and so k equals 0 term will be, so k equal to 0 term will be this rectangular starting from 0 to omega naught, and k equal to, sorry, so then it is 2 omega naught. Okay, so k equal to 0 term will be will be the summation of this first rectangular, and k equal to 1 term will be the will be the area of the second rectangle, and k equals 3 term, etc. So we see that this k minus infinity to plus infinity term is this rectangular approximation of area under the curve. And when you take the limit of omega naught equal to 0, that's what happens when you t go to infinity. Then the summation actually becomes just the integral of this function. Okay, so that's x of j, big X of j omega e to j omega t d omega, and we have 1 over 2 pi. Okay, so that's the derivation. That's the big T goes to infinity. So maybe I should write t goes to infinity. T go to we already have it there. Yeah, so as big T goes to infinity, x tilde of t become x of t, and the summation become the integral. Okay, and so so this complete our derivation of our Fourier transform. Okay. So once again, we have two equations, our synthesis equation and the analysis equation. Okay. So x of t is the integration of big X of j omega e to the j omega t d omega, okay, times 1 over 2 pi. And big X of j omega equal to integration minus infinity to plus infinity, x of t e to the minus j omega t dt. And I guess here you can kind of see, so you see big X of j omega is kind of the coefficient for e to the j omega t. So x is x of t. You can think of is summation of all those components of e to the j omega t for every possible omega. So omega from minus infinity to plus infinity. But there are just too many of them, so instead of a summation, we take an integral. And somehow we have a big X over 2 pi instead of big X, just because that's our convention. Okay. So, so big X of j omega is the coefficient of e to the j omega t, kind of. And that's kind of why you have j omega here, because you have j omega here. And so this is a synthesis equation. You write x of t as a linear combination of e to j omega t, and sum over all possible omega. And then you have the analysis equation of how you calculate this big X of j omega. Is you do x of t and you multiply by a very similar thing into a minus j omega t, and you just integrate it over t. And so this big X of j omega is very important. This is called the Fourier transform, or Fourier integral, or the spectrum of x of t. So we kind of think that the transformation is a back force between x of t and the big X of j omega, and often we call this x of t as a time domain signal, and the big X of j omega as a frequency domain signal. Okay. Okay. And so because big X is the Fourier transform, so actually the 4.9 is called the Fourier transform equation, and 4.8 is called the inverse Fourier transform equation, and those together are called the Fourier transform pairs. Okay, so a bit of recap here. So inverse Fourier transform and the Fourier transform, and we have derived this from Fourier series, and take big T to infinity. Okay, and so basically this is all you need for chapter 4. If you are really good at integration, then you can calculate everything from those two equations. But obviously we are going to talk about more properties. And I think this is a good time to stop here right now. And any questions so far? It's about derivation or meaning of the Fourier transform and the inverse Fourier transform. Okay, not? Okay. So anyway, so those are the famous Fourier transform pairs. Okay, the continuous Fourier transform, and once again, it's for a periodic signal. But we'll soon see that. Maybe on Friday we'll see that we can actually also use Fourier transform periodic signal. Kind of funny. But for now, let's go back to a big comparison. So so what I've done here is we start with Fourier series. So Fourier series is this transformation between x of t and ak, and then we take a big T to infinity, and we kind of think then we are sampling those k omega naught point to continuous. So we think this k omega naught is a frequency, and then when t goes to infinity, omega naught goes to 0. So we basically take every possible omega. And so instead of a transformation between x of t and ak, you have the x of t to this big X over j omega, okay, so I should say this, so I should write better. So we have a big X over j omega with omega equal to k omega naught. Okay. So this is what happened in this chapter. We have a periodic X, and we get this big X of j omega. Okay. And so basically we are getting all possible complex exponential in our synthesis. Okay. And then one more thing, kind of supplement material is different convention. So those are things that we don't use in our test or homework, but you might see in other books. Okay. So once again, there are different conventions for Fourier transform. And once you see is, so remember in our equation, you have this weird symmetry. So we have 1 over 2 pi here and nothing here. And turns out you can push this 1 over 2 pi everywhere. So some people push 1 over 2 pi here. and if you like more symmetry, you can put the square root at both of the equation. And also sometimes instead of omega, people like I guess also frequency, but frequency instead of a radian, frequency in terms of how many rotations. So we can have this big F frequency. Okay. So those are different notation. You might see different books. So just be careful when you see Fourier transform formula. You need to know what's everyone's convention. Okay. No question. Then let's go to the convergence issue. Okay. And just like a continuous time Fourier series, Fourier continuous time Fourier transform also have convergence issue. Okay, and so what we want to check is if we take it as x of t, now it's a periodic signal, and then use this equation for 8.9. So you put in x of t, you do the integration, you get some big X of j omega, and then use 4.8 to get some x hat. Okay, so you get some x hat from this big X of j omega, and then you want to know that. So first of all, does both of these integration converge? And second of all, does x of t equal to this x hat, where you just transform to big X and transform back? Okay, so So this is a convergence issue question. Okay. I guess I should note here. And so does x hat exist? So first x hat need to exist. Also, okay. So first x hat need to exist, and then we want x hat equal to x of t. So this transformation back and forth actually makes sense. So yeah, and similar to the periodic case where we have Fourier series, we have some condition that make the transformation back and forth make sense. Sometimes it just doesn't make sense. For example, we have very bad function, then this integration will just not converge. Okay, but a lot of time it converge, and then x hat of t also just like in the series Fourier series example, they will not exactly equal, but they will equal in some sense. For example, we can have this energy equal. So so we can say one can prove that. Here we state without proof. So your xt has finite energy, means that is energy over the whole time from minus infinity to plus infinity is some finite number. Then you can guarantee that the difference, so the difference between x hat and x of t, the energy of this difference will also be 0. Okay. And but this doesn't mean the two functions are same at every point. So maybe they have. So one example is a very bad example, I guess. But so maybe your x of t equal to 1 is 1 over this point at 1, and there is 0 everywhere. Okay. And x hat of t will probably look like 0 r everywhere. Okay. And so at this point 0, you will see that at this point 0, x of t not equal to x hat of t. But because this is just a single point, when you take a difference and do integration, then the energy will be 0. Okay. So we can have this very weird discontinuous disparity between xt and x hat of t. But we think if the difference of the energy of the difference is 0, then they are the same signal for engineers. Okay. And also similar to this periodic case, we have the Dirichlet condition. So Dirichlet condition says that they are equal for every t. But just like before, this is for every t, but there can be Gibbs phenomena. Yeah, so it's for every t there is some big N that they are equal. Yeah. But anyway, the the differential conditions are also similar. So x of t needs to be absolutely integrable, and this time means integration from minus infinity to plus infinity, this absolute value. And x of t has a finite maximum and minimum, and has finite discontinuity. Okay. And those are within any finite interval. Okay. And so we just stay with our proof. And you can check the functions we have, and that they are all behave pretty nicely with respect to this. So basically everything we do in the class will be convergent. Okay. And okay, so I guess let's go to the more interesting part of we actually see some example of Fourier transform. Okay. And so we start with this exponential in decay function. So x of t equal to e to the minus at and u of t. So it cut off at t equal to 0, and then we have this exponential decay, where our a is some positive real number, so it's actually decaying. Okay. And so yeah, so what's our frequency? Our Fourier transform for x of t is we do the integration. Okay, so we take x of t, so it's this equation, right? And so we just take this x of t and multiply e to the minus j omega t and do an integration. So integration, because it cut off at 0, so from 0 to plus infinity. And yeah. And then it's just standard calculus here. So e to the minus 8 plus j omega t. And so you have minus 1. And so integration over this exponential, you have this 1 over the coefficient, so minus 1 over a plus j omega, and the boundary is infinity and 0. Okay. And because of this minus a here, so you have the minus real a, so the infinity this is 0, so and the 0 is 1, and the 0 is 1, so and you get 1 over a plus j omega. And this only happens when a is bigger than 0, because you need a bigger than 0 for your infinity to be 0. Okay. And so we can kind of plot this. This is a complex function. This once again is a function of omega, and has some parameter a here. And we can apply the magnitude and its angle, because it's a complex number. And you see the magnitude is kind of decaying with omega. And you see that when a is bigger, then this peak is wider. Okay. It kind of makes sense, because when a is so intuitively it means, because if a is bigger, then this thing is decaying faster. Then if you want to decay faster, then you need some higher frequency component, because it will change faster. Okay. So if a is bigger, then you have your spectra being a wider function that includes more high frequency component. And also we have an angle here. Angle is just a complex angle. Okay. And then we can generalize this a little bit. So we kind of say that a needs to be bigger than 0, but actually a don't need to be a real number totally. So a can be a complex number, and sometimes it is still integrable. And so you want this to still converge, then you basically need this infinity to be 0, and what you need is only the real part of a to be 0. Okay. So if the real part of a is 0, then the integration still works through, and so we will get the same integration result, and the big X of j omega is 1 over a plus j omega. Okay. And this is actually a very useful function. We'll see this more in chapter 9, where we talk about Laplace transform. Okay. So that's our first example. Any question? Oh, go ahead. 4.9是 Fourier transform， 4.8是 inverse Fourier transform。虽然我是不会直接考，但讲起来应该是这样。因为老师的定义和那个就是你在上面的 投影片有改过对不对？但是应该是没有错，因为我的投影片本来是相反的，你自己看的话，嗯，anyway，对，4.9是 Fourier transform，4.8是 inverse，我会把这个新版的 po 上去，抱歉，这还没有，对，但应该写的是没错的，一样的，这有点混乱，嗯，OK，有问题吗？OK，那我们剩10分钟，OK，那我们可以看，OK，we have about 10 minutes. We can go to the oh, sorry, too far. Okay, we can go through. Here's one or two more example. Okay, so now we go to another example that's kind of funny. Okay, we have our example of xot equal to delta function. Delta function is kind of funny because it's not quite a function, it has this infinity. But I guess technically it kind of satisfy the rational condition, but not quite, it has infinity. But anyway, we can try to put it inside our, Fourier transform pairs and see what happens. And then we see the integration actually works through. Okay? So yeah, so you have big X of j omega is integration x of t to minus j omega t dt, and now x of t is this delta function here. Okay, and then we find out that we can do this integration because delta function, we just have this nice shifting property where you have delta f of t times delta of t, you do integration, you just pick out f of 0. And f is this e to the minus j omega t, so you just have e to the minus j omega 0, which is equal to 1. Okay, so big X is this constant function. Okay, so we see that, the first interpretation here is we have delta of t, and then you do Fourier transform, then it becomes this constant function, constant 1 function, and means that it is a constant for all frequency. Okay, really nice. And then something funny here is you find out that, okay, so maybe that's just right here. Okay, and so something funny is we actually think this is a legit x of t and the big X of j omega pair. That means you can find x over t from big X of j omega here, and that means that we think this funny integration 1 over 2 pi minus infinity to plus infinity, and just 1, so x of j omega equals 1, and e to the j omega t dt, j omega t d omega, we think this is equal to delta of t. Okay, and now this integration doesn't look so convergent, and so if you are really rigorous, you need ways to argue why this is true. And now it gets kind of circular, and one way to argue it is we think these two are very Fourier transform pair. But anyway, so this is a funny interpretation we get here. And even though this x of j omega, it doesn't quite satisfy the rational condition because it's not absolutely integrable. You try to integrate this, it's infinity. And but we still think this equation holds. So 1 over 2 pi integral minus infinity plus infinity to j omega t d omega, we think is the delta function. And you can see this integration doesn't quite work because you don't get a nice finite function. You get this delta function here. But anyway, this is what we think is true. Okay, and I guess the bottom line is we just kind of recognize the delta of t and one Fourier transform pair. Okay, and okay, let's go to next example. That's less divergent. That's x of t equal to our favorite block wave signal. Okay, and so we have seen similar thing in chapter 3 where we have this thing periodic. But now we only have one block wave here. So x of t is 1 from minus big T1 to big T1, and 0 elsewhere. And once again, we can calculate our big X of j omega, And now this is a very convergence integral. Okay, so big X over omega, I just minus t1 to t1 e to the j omega t dt. And you do the integration, then you see this is sine omega over omega c. Okay, and you plot it, and you look at this. Okay, and then it has it has a weird point of what happened when omega equals 0. And when omega equals 0, this function actually equal to t1 and multiplied by 2, so it's 2t1. And you can also just take omega equals 0 here and do integration, and you see it should be 2t1. Okay, and okay, so I guess the integration from x over t to big X over omega is okay, but if you try to do the reverse, then you have some convergence issue. Okay, so even though these two functions are very nice, both of them satisfy the Dirichlet conditions, but just like in this Shukan case, so you try to integrate this big X over j omega back to x over t, and you have some finite cutoff, then you see that you will have the Gibbs phenomena. So the function you add back, you will have some repose on the edge. Okay, and so that means if you try to transform this back, then you get a function that gets some repose at the edge. Okay, and that makes sense because just like in the periodic case, because when you integrate this signal back, you're basically adding continuous components, and so yeah, you're adding continuous components, and so you expect all the edges to be rough, and when you have this sharp discontinuity here, then you will get some ripple effect, and that's a Gibbs phenomenon that we have described in chapter 3. Okay, so similar, and let's just say it exists, and we ignore them. Okay, and then okay, so this is for now. This thing is kind of similar to chapter 3, and in the next 1 minute, let's do something funny. Okay. And we'll continue on Friday. But let's do something funny. That is, in a continuous case, we can actually kind of reverse the time domain and the frequency domain. So now we think about if we have a signal that frequency domain look like this square wave. So it's 1 between this big W minus big W to big W and 0 otherwhere. And we can calculate x of t, and so we can calculate x of t through this equation, and we see that it has a similar form, right? Because basically you do a similar integration. It's both is integration of either e to the minus j omega t or e to the plus j omega t, but the result is real, so actually plus and minus doesn't matter. Okay, so if you start with your frequency domain here, and you do inverse Fourier transform, and you see your time domain is actually once again is sine t over t function. So basically sine something over something function. Okay, and in this time is sine w of t over pi t. Actually we have a little more minutes. Okay. Then yeah, we'll talk about this symmetry in more detail later. But what we have seen here is it's basically this, but we see that the time domain and the frequency domain of this continuous Fourier transform have interesting symmetry. So you have this signal, time domain signal transform to frequency domain signal. Then you can kind of flip them on each side, and you see a similar signal on time. So you swap this signal to the time domain, and you see its Fourier transform is a similar signal in frequency domain. And yeah, so time and the frequency domain has this interesting symmetry on continuous time Fourier transform. This is just basically comes from, let's go back to our equation. That basically just comes from our equation has a very nice symmetry. So you see those two equations looks very similar. You just have a difference in a minus sign here and a difference in 2 pi here. Okay. So yeah, that's symmetry between time and the frequency domain, and That's the Fourier transform of the square wave. Okay, a periodic square wave. And we are exactly on time, so let's continue our discussion here. Next on Friday. Okay, so see you on Friday.